So today we're going to be extending our work in vectors and actually doing some arithmetic or some math operations, some arithmetic operations with vectors. We are going to be all about finding resultant vectors today. And a perfect observance of this or real-world observation of vectors in play is right here. We got some kind of large plane, probably a 737, doesn't really matter, but anybody want to talk about what they're observing between the direction that this plane is pointed in and the runway?
He does not know how to land.
This pilot knows very much how to land. His tail is way to the right. That plane is pointing in a completely different direction than the runway. And just proved that she's never been in a boat on water or tried to ride a bike in the wind. This plane has a runway that needs to land down. Now, I'm going to write this in terms of vectors. This vector is not the length of the runway, but this plane, every plane has a minimum stall speed. If they go below a certain speed, they're going to stall and crash. You can land at a speed greater than your stall speed, but not much above it. So this plane has to slow down to a point where it can still safely fly, especially in these horrible conditions, and be yet slow enough to be able to land. So this pilot needs to land the plane, not slow down so much that he stalls and crashes, or he or she, and not so fast that it's physically, impossible to land this plane because there's too much lift created by the wings. But there is a vector that you could consider going in the direction of that runway. That vector is going to have a certain angle, and that vector is going to have a certain length. That length is not going to be the length of the runway. That length is going to represent some kind of speed, some kind of velocity. Arguably, probably speed for the purpose of this, because if you're going up or to the right, velocity is going to be considered positive, and if you're going left or down, that velocity is going to be considered negative. So there's going to be some kind of speed. So there is a resultant vector that needs to happen between the plane, which is pointing in basically this direction, and the wind, which I probably have this backwards from the orientation of this situation, but there is a force vector that's being created by the plane, and the reason why that plane is pointed in a different direction than the runway is not because the pilot's trying to be fancy or doesn't know how to fly. That pilot is trying to fight the force of the wind that's trying to push it off course. There is a wind vector, which will also have its own angle of rotation or direction and its own magnitude. We talked about yesterday there's only two things that define a vector, which is what? Direction and magnitude. So there is a plane putting force in this direction, fighting a wind that is going in, let's say, just for convenience sake, this direction. And together, between the force, the direction the plane is pointed in, and the force that's being created by its engines, and the direction and force of the wind fighting, basically in this case, against that plane, that when you take vector, let's say u, and you add it with vector v, you get a resultant vector, which is that vector, that sum of the force and the direction from the plane added with the force and the direction of the wind, and that plane safely going down the runway. So there is a vector representing the force of the plane, there is a vector representing the force and direction of the wind, and then ultimately that plane needs to land on the runway, safely, as in not running off the runway somewhere, not getting blown, not having the wind blow so hard that it's pushing it off course, not fighting so so much against the wind that that plane actually overcorrects and goes off the runway in this direction. There is a live battle of two vectors that needs to create a third resultant vector that puts that plane safely on the runway. Now, so what we're going to do today is go between vectors in component form and vectors as they are described by direction and magnitude. So we're going to start off easy and just talk about, how do you define a resultant vector? How do you add vectors? We're going to start geometrically. So, let's just say that we have this vector u that's about that length going in a direction of 90 degrees. Let's say that we have vector v, which is maybe that length and going in that direction. Now, if I want to draw the resultant of, let's say, 2 times vector u plus vector v, just as a geometric drawing, no math, we are going to be taking this vector u and applying a multiple of 2, a scalar multiple of 2. So if this is u, let's say, I don't know, whatever this is, about that long, 4 or 5 inches, and we want to work with a vector that's 2 times that length, that 2u, that's a scalar multiple that will change the length of the vector by a multiple of 2. So if this is vector u, then let's say that this is approximately 2 times vector u. And if we want to add that with vector v, then I have 2 ways of doing this. I can use my preferred method, which is called the triangular method, though we're going to work with more than 2 vectors at a time, so we're not always going to be drawing triangles. But I can write out 2 times vector u, so we're going up and going twice as far, and I'm approximating all this, just a visual sketch, of course. And that's vector v. And the triangular method is where you're just reading your expression left to right, just following those order of operations and drawing your vectors as you go. So 2 times vector u, the resultant vector, the vector of 2u, 2 times vector u, plus vector v, is going to be drawn by starting from wherever you started the drawing, that first initial point, and ending at your last terminal point. So that right there is 2 times vector u plus vector v. And we are going to basically only be doing drawing resultant vectors with this sort of like triangular method. Now, there is another way of doing this problem, another way of drawing out this diagram, which is, instead of the triangular method, you can do this only when you are adding 2 vectors. I can draw 2 times vector u plus vector v by drawing both of those vectors with their initial point at the same point. So again, vector u is about whatever that is, 4 or 5 inches long. I'm going to approximate that length doubled. So, and it's only a sketch, so let's say within reason that that's vector 2u. I'm going to add that with vector v, but this time what I'm going to do is I'm going to give vector v the same initial point as vector 2u and get something that looks like this. Okay, so that is also a way of drawing, starting the process of visualizing or drawing a resultant vector. Now, this is the parallelogram method. And what do you know about parallelograms? Their opposite sides are parallel and equal, or in length. So now what I have to do with this drawing is basically draw the other half of the parallelogram. So I'm going to try and draw an opposite side that are the same length and have the same direction. And then once the parallelogram is finished, draw a diagonal through that parallelogram. And so this is, and hopefully it looks basically the same, but this isn't on Desmos or a computer, and I don't even have a piece of graph paper up here or a graph paper grid because I have a whiteboard, not a chalkboard like I wish I had. These are both reasonable representations of what that resultant vector looks like. Now, the reason why the triangular method is very much preferred is because you can very often be working in situations, especially like in physics, if you're doing advanced physics, or even in this book, there might be 3 vectors. So there may be like an additional vector of W. Now, if I want to draw, as my third example here basically, if I want to draw the resultant vector of vector u plus vector v, so vector u plus vector v minus vector w, you're not going to draw a parallelogram when you have 3 vectors that are all starting with the initial point. So if you have 2 forces working together in the same problem and you need a resultant, you have an option between drawing out your resultant with a triangular method or a parallelogram method. But as soon as you get more than 2, like you have 3 vectors here, your only option for drawing the resultant vector is going to be the triangular method. Now there's going to be a good reason you want to do this, which I'm going to explain after I finish this drawing. All right, so we're not going to change the length of u. Let's just kind of try and keep it the same. I'm not going to break out, use my fingers here, about that long. Okay, yeah, whatever. About that long. So let's say that is vector u, right? Initial point, terminal point, the direction was 90 degrees, or at least it's basically looked like it's going straight up. Vector v is a little bit shorter, maybe say 50 degrees or so, but we're just eyeballing these sketches. That's vector v. Now here comes vector w, which, so I have something nice to look at. Let's make that a little bit longer. I want to draw not the addition of vector w. I don't want to go in the same sort of like direction of the given little like sketch vector. This is a minus w, basically applying a scalar multiple of -1 to this vector w. So we're going to take that vector and move and pop it into the opposite direction. So whereas vector w in its sort of original format kind of looks like this, length going to the right, since we're subtracting w, we're going in the opposite direction, the opposite vector. Like, an angle going 30 degrees and an angle going 210 degrees are going in opposite directions. Instead of quadrant 1, you're going into quadrant 3. So this is a subtraction of vector w. So then how do we draw the resultant vector? Go to the first initial point and end at the last terminal point. That's it. So this is the resultant vector. This blue vector is vector u plus vector v minus vector w. As we're given real-life applications like that plane landing or tugboats pulling a barge in a certain direction, if you draw a good resultant vector to reasonable scale, you'll be able to understand if your final answer in component form is valid or not. So we didn't do any math to this, but let's just say I told you that vector u plus vector v minus vector w in component form. Now this is only 2-space, don't get fancy on it. Let's say that in component form I got 1, 5 as my final answer. And let's say that my drawing of the resultant is, good enough. It's not down to like the nearest degree or anything like that. I didn't break out a protractor or Desmos, but I tried my best to make it an accurate drawing. Would this be, and give me a reason, would this be a reasonable final answer if I actually did some work in here? Like if I gave you these three vectors in component form, or you had to write these vectors in component form before you added them, but you did some math and this was your answer. Is this reasonable? What defines a vector? Magnitude and direction. So your movement, your initial point does not have to be the origin, but in component form, right, your component form of a vector, this is some kind of A component over B component. This is some kind of A comma B to match the notation of the book. This is some kind of A times vector I plus B times vector J. And we talked about how A is a movement in what direction? Horizontal. And B is like a movement in the vertical direction. Why do we not call this X and Y?
Because they're not vectors not defined by its position.
Yeah, vectors are not defined by their position. We're not moving off of the origin. But what if this were a little, let this be an origin? Why is this not reasonable?
The A value comes from negative.
This is a movement to the right and up. If your initial point is the origin, you need to be pointing up into quadrant 1. Our resultant vector is pointing up to the left. If this were the origin, you'd be in quadrant 2 where the A values, your X values are negative. Now that would be a reasonable answer. If I did some math to these vectors and I got a resultant of negative 1, 5, saying that I'm moving left and up from my initial point, this is good enough to make it, it's not an absolute check, but at least I can say it's reasonable. So you do want to be able to sketch a resultant vector for your problems that you have in your homework. Okay, so let's take a look at some examples. Vector operations, adding and subtracting vectors, needs to be done in component form. So, okay, this is going to encompass everything that you're possibly going to need to do with vectors. So there's a lot in this question, starting with the fact that we don't have a drawing. So a plane flies at a speed of 180 miles per hour on a bearing of north 50 east. That's going to be one vector. And the wind is blowing from west to east at 40 miles per hour. So we need to start somewhere. What general direction is this plane going? Wrong. North 50 degrees east. Where's north? Up. Where's east? To the right. So we're going to start referencing the north line and rotate 50 degrees towards the eastern direction. So this plane is flying basically up and to the right. And I need to draw this diagram. So I'm going to draw a diagram with some room for me to go up and to the right. So there's a north-south line. I'm going to try and make this nice and big so I can, have room to write some numbers. 50 degrees is a little bit more than 45, so maybe somewhere in this direction. And that's going to be the plane. I'm going to relate the plane to be vector v. And this vector has an angle of 50 degrees between north and the actual direction that the plane is pointed in. That length is going to be 180 miles per hour. So the magnitude of vector v is going to be 180 miles per hour. And the angle for theta, how does your computer, your calculator, how does technology measure angles? How do you measure a standard position angle? It's not from due north clockwise. It's what? From the positive side of the x-axis counterclockwise. So we need this angle theta. So if it's north 50 degrees east, what's theta off of the positive side of the x-axis? Not that this has to be the origin.
40.
Yeah, of course, it's 40 degrees. Okay, great. Well, here comes the wind. The wind is coming in coming from the west and going east. So if you're coming from the west and you're going east, where's the wind going? To the right. So we got a little bit of a break here. They're not getting fancy about the bearing of the wind. It's going towards the east. So you have a wind vector. And that wind vector is going in this direction. So that wind vector has a theta of what? Okay, so the wind has a bearing of, let's say, 90 degrees, but the angle, the direction your calculator is going to understand is the theta 0. The bearing of the wind is 90 degrees because that's due north and you measure bearing in a clockwise direction, but your calculator does not know bearing. Your calculator knows standard position angles. So the wind has a bearing of 90 degrees. The wind is going west to east, but the theta that you will put into your calculator is 0. What is the speed of the wind? So since the speed of the wind is 40 miles an hour, the magnitude of vector W, W for wind, see what I did there, is going to be equal to 40. Now, if that plane wants to fly north 50 degrees east, it's got a problem because it's getting pushed off course by the wind. Or, hopefully, the pilot actually does intend to go in the direction of the resultant vector, and that pilot is actively fighting the effect of the wind throughout the entire flight, which is exactly what they have to do. So that green vector, it's a little crooked, but that green vector is the resultant vector. That green vector is vector v plus vector w. We need to find that resultant vector. Problem. We don't have any of our vectors in component form. So I'm going to need some of you to help me out. So I'm going to come over here and do some scratch work. We've got the plane. We've got vector v. We've got a vector that has a length of 180 and an angle of 40 degrees. We need the components of this vector. We need vector A. Well, we need the horizontal component, and we need the vertical component. How do we find A? So we have the cosine of 40 degrees is equal to A over 180, which means the horizontal component. Can somebody give me some help? I need your calculator in degree mode, and I need 180 times the cosine of 40. What's the horizontal component?
137.9.
Cool. All right, same thing, but now we need to find B. How do we find the vertical component? Sine. So the sine of 40 degrees is equal to B over 180. So B is equal to 180 times the sine of 40 degrees. And B is approximately equal to 115.7. So now we know that vector V in component form, describing the force and direction that the plane is, the speed and the direction of the plane, in component form is 137.9, 115.7. What is going to be the vector describing the wind? We really should not have to do any work for this, because this basically the wind vector is sort of like, it's really a quadrantal angle that we studied in chapter 4. You're moving horizontally from its sort of its own little personal origin. What's the horizontal component? 40. What's the vertical component? 0. So the wind vector in component form is 40, 0. So now these two forces are working together. The engines, the plane's engines and the wind is creating this resultant direction. So this plane's actual trajectory vector, vector v plus vector w, is 137.9 plus 40, or 177.9 as a horizontal component, and has a vertical component of 115.7. And these are both in miles per hour, basically, because the wind and the plane are being described as, you know, their speed in miles per hour. Well, that's great, but, you know, that doesn't tell us what the ground speed of the plane is. That doesn't really tell us the direction. Like, it's great for math, but no one's going to understand this except for like another mathematician or somebody that knows trig. So let's put this back into plain language. Okay? What is beta? What is, okay, it won't be bearing yet, but what's the direction of the plane? What is the magnitude of this resultant vector, which will be the speed of that plane? So now so in this problem, which is not an easy problem, it could be a little bit harder, but it could be worse or easier. We have gone from what describes vectors? Magnitude and direction. We went from magnitude direction and did a little review of how to go into component form. We have added two vectors in component form without really teaching or showing you the formula in the book. We just naturally added the horizontal components. I guess I just sort of just said it. And we added the vertical components. And now we're going from component form back into sort of what I would call plain language. This component form is great for math. It's not great for like describing anything to someone that, you know, just explain this in like plain English. Where are you going and how fast are you going? So what is the magnitude of the plane? How do you find the magnitude of a vector? The magnitude of a vector, somebody talk to me in a second. And I'm going to have to call plane operations and find out why my room's still freaking blazing hot. How do you find the length of a vector? It is a right triangle. Yep. It's the square root of a squared plus b squared. So it's going to be the square root of 177.9 squared plus 115.7 squared. And that magnitude is going to be approximately equal to 212 miles per hour. So as far as the plane is concerned, it flying through the air is registering an airspeed of 180 miles per hour. But it's not directly fighting against the wind. You know, there is some like movement to the right in the trajectory of the plane, and that is also kind of like, it's sort of pointing what? Northeast, and the wind is going east. So that wind is actually, though the plane is fighting it a little bit, is creating a ground speed that's a little bit higher than what's registered by the airspeed. So the ground speed is 212 miles an hour. Just Pythagorean theorem.
So the magnitude, if that's equal to speed, that would be the magnitude?
Everything in this particular problem, you were given the speed of the plane, you were given the speed of the wind, and the resultant will then therefore be a speed. You could have vectors describing pounds of force on an object. Your vectors could really arguably be representing any type of force in our environment. For this question, it is representing miles per hour.
And then the direction was the vector v plus.
Well, we haven't found that yet. We do have this green resultant vector that we that we drew by drawing the vector representing the plane and the vector representing the wind, we haven't actually found the new direction yet, and I'm out of time. How will we, let's just write this, let me hit pause, this will take like 2 minutes to write. How will we find beta? This is a right triangle. You don't have to use all your brand new tools because they're cool.
You just do arctangent.
Tangent. So the tangent of beta is equal to the opposite leg of 115.7 divided by the adjacent leg of 177.9. Beta is going to be the inverse tangent of that, meaning beta is going to be 32.9 degrees. Now, I'm not going to hold you any longer because that would be not very nice. But then that's the angle, not the bearing. We don't have the bearing yet. That's off of due north, but that is the direction. Have a good one. Now that we have our direction angle for the resultant vector of the plane flying against that or flying with that crosswind, and knowing that beta is 32.9 degrees, remembering that while technology works with standard position angles, which start from the positive side of the x-axis and rotate in a counterclockwise, this problem gave us bearing in the first place, so we're going to want to say that our final answer, the bearing of this plane, you know, the number that the pilot is seeing basically on the compass, is referencing north. We are rotating a certain number of angles, a certain number of degrees east of north, and our bearing is going to be north, taking 32.9 degrees and subtracting that from 90, because there's a 90-degree angle between north and east. We're going to have a bearing of north, 57.1 degrees east. And that is the end of our example. Well, you guys are a great class. Here. All right, so here we go. We've got an object that weighs 20,240 pounds, being suspended in the air by a couple of cranes, one on the left and one on the right. We'll call the left vector v and the right vector u. And if this object is suspended in space, how many vectors are in this system? 3. Just like when we hung the picture on the wall, there are going to be 3 vectors. So we'll call the weight of the object vector w. So what does the sum of these 3 vectors need to be?
0.
Exactly. If this object is not moving, then it needs to be in equilibrium, and that means all the forces are adding up to 0. And then if we know what forces it takes to hold this suspended in space without moving, then we can adjust, you know, tension, force, whatever on the cables to move this wherever we want. To add these 3 vectors up and make sure that they are in equilibrium, to make sure or find the solution so that the sum is 0, what do we need to do? How do we need to write each of these 3 vectors? Ethan?
Say again?
Math of vectors, vector operations. When we want to find a resultant vector, when we want to add vectors, what are those how do we need to write those vectors? There you go. So keep helping me out then. If the angle to horizontal in the diagram is indicated to be 24.3 degrees, what or how do we find the direction for vector v?
Well, you subtract it from 90 by like 5 centimeters.
While that might be an angle that you could make work, I want you to talk about like the amount of rotation, how we studied angles in chapter 4. Standard position angles, how do we start that rotation? What is the angle? What is theta from, what's the direction? What is theta for vector v?
Subtract from 180.
There you go. So for vector v, thank you, sir. So for vector v, we have, a magnitude which is unknown. That's what the question is about. But vector v has a direction which is equal to 180 minus 20 is 160. 160 minus 4 is 156. And now we're at 155.7. Vector v has a pair of orthogonal angles which are the component form, the horizontal and vertical movement. So understanding that we have an angle of 155.7 degrees, how do we find the horizontal component of vector v? Somebody help me out. It's going to be the cosine of 155.7 degrees is equal to the adjacent, or sort of the pseudo x, if you will. What defines a vector? Direction and magnitude, not its location. But we are still doing the exact same trig that we learned how to do in chapter 4. So if you want to think about this point as it's, some like the temporary, our own little personal origin here, we just want to do the cosine is x over r and sine is y over r. We're just not using the labels of x and y because this doesn't have to be the origin. But if you think of it temporarily as being the origin, you can just use those x, y, r ratios we learned in chapter 4. So the cosine of theta is x, or in this case a, over r, but we're not talking about radiuses of circle, we're talking about lengths of vectors. So this is going to be the magnitude of vector v. And so a is equal to the magnitude of vector v times the cosine of 155.7. So likewise then, how do we find the vertical component? So the sine of, what's the angle? What's theta for this vector? 155.7. Yep, so the sine of 155.7 is equal to the vertical component, which in chapter 4 and 5 we called y. Now we're calling it b. Over the hypotenuse, we were calling it r. Now it's the
vector
magnitude of the vector. So same thing, fancier labels. So b is going to be the magnitude of vector v times the sine of 155.7 degrees. So vector v, let's get back to black so it's easier to see. Vector v in component form is the magnitude of vector v times the cosine of 155.7, and the vertical component is the magnitude of v times the sine of 155.7. How do we do the same thing on the other side? The angle of the other cable is indicated to be at a direction of 44.5 degrees. So we're going to say that vector u has an angle of 44.5 degrees. So how do I find the horizontal component for vector u?
horizontal would be cosine of 44.5.
Yep. So we have the cosine of 44.5 is equal to a over the magnitude of vector u. So a is the magnitude of vector u times the cosine of 44.5. And likewise, then the vertical component is going to be the sine of 44.5 is b over the magnitude of vector u. So b is the magnitude of vector u times the sine of 44.5. And again, I'll write this in black so it's easier to see. Vector u in component form is the magnitude of vector u times the cosine of 44.5. And the vertical component is the magnitude of vector u. So what's vector w in component form? What is the component form of that vector? This object weighs 20,000 20,240 pounds. It's in the air. So if these cables get released, where's that box going? Straight down. So what's the horizontal component? So vector W has a horizontal component of 0. But you did say it's going to go down, and it's going to go down with a weight of 20,240 pounds, but it's down, not up. So what's the vertical component?
Negative 11,000.
Cool. Okay. The sum of vector V plus vector W plus vector, the sum of vector V plus vector U plus vector W, what's the sum of these three vectors going to equal if this object is being suspended without moving? 0. Okay, it needs to be in equilibrium. So the magnitude of vector V times the cosine of 155.7 plus the magnitude of vector U, the horizontal component of vector U, which is the magnitude of vector U times the cosine of 44.5 plus 0 needs to be 0. And the vertical components also have to be 0. So vector V times the sine of 155.7, I don't know why I used parentheses there, plus the vertical component of vector U, which is the magnitude of vector U times the sine of 44.5, plus the vertical component of vector W, which is negative 20,240, also has to equal 0. So the sum of these two vectors needs to be 0. So the sum of the horizontal and vertical components both need to come out to be 0. Now, I can just take this negative 20,240 pounds. I can take that negative number, just move it over to the right with addition. So I'm going to do that. I'm going to add both sides by 20,240 and get that the magnitude of vector V times the sine of 155.7 plus the magnitude of vector U times the sine of 44.5 is equal to 20,240 pounds. Anybody know how we're going to solve this problem? Okay, let me ask you this then. Is the cosine of 155.7 just a number or a function? What do you get from the cosine of 155.7? So we're going to get a number or a variable? A number. So this is just going to give you a number, like maybe it's 2. And do we know what the magnitude of V is? No, it's an unknown. It's just an x. What's the cosine of 44.5 going to be? Some number. Not the same number, but some number. And it's positive, so maybe like a 5. Of course it's not. I'm just making this up randomly. Do we know what the magnitude of vector U is? No, it's just an unknown. And there's no powers. Like, this isn't the magnitude of vector V squared or cubed or square rooted. It's just an unknown magnitude. So this is a number times a variable plus a number times another variable. And that's equal to 0. And the sine of 155.7 is just going to be a number times some variable that I've already called in this silly little example. I've replaced the magnitude of vector V with like an x. So the sine of 155.7 is just some number. I don't know what it is. It certainly will not be this number. But, you know, basically, if you can realize that all you're looking at in this ugly looking equation with this fancy magnitude of vector notation and all the trig, it's just a linear system of equations. And how did you solve linear systems of equations at the end of Algebra 1 and beginning of Algebra 2? Linear combination or substitution, where you pick the simplest. Now, of course, all this is going to be kind of gross, but you're going to pick a variable to solve for, So maybe you're going to solve this for x, and once you get that expression, you're going to plug it into the other equation. You're just going to do like probably a substitution method. If it was way back in like this kind of setting, I would be trying to find opposite coefficients in front of x. I'd be doing the linear combination process. But these are gross numbers. That's probably not going to work. Now, just to make this more palatable, in my notes in my iPad, I've got all this left. I have all of this left in exact format, and I don't type it in the calculator till the very, very end. So there's no round-off error. But I think this is going to be much more palatable if we just let us have some numbers. So what is the cosine of 155.7? So 9,114?
Yeah.
Okay. So that is negative 0.9114 times the magnitude of vector v. And what is the cosine of 44.5? Just, I know you already have this, so just start reading these out. All right, so let's take the first equation because there's a 0 here. Let's solve this for vector v. So we're going to have negative 0.9114 times the magnitude of vector v is equal to negative, because I'm subtracting this over to the other side, so negative 0.7133. Is that the right decimal? So then that is times the magnitude of vector u. So let's divide both sides by negative 0.9114. So the magnitude of vector v is equal to, so 0.7826 times the magnitude of vector u. So now we know what vector v is. And now we're going to take that answer for the magnitude of vector v and plug it into the other equation, right? We're solving by substitution method. And I'm also clearly going to run out of space. So, so we're going to take this now and plug it into the second equation and get 0.4115 times the magnitude of vector v, which we now know is 0.7826 times the magnitude of vector u, plus 0.7009 times the magnitude of vector u is equal to 20,240. Now my notes don't have all these rounded off decimals, so I need your help. These are going to be like terms, right? Magnitude of vector u, magnitude of vector u. So what I need somebody to do with their calculator is 0.4115 times 0.7826 plus 0.7009. Okay, so we got 1.023 times the magnitude of vector u is equal to 20,240. Divide that both sides by 1.023 and we have the magnitude of vector u is what? 19,784.95 pounds. So far we've got that vector u needs to be exerting a force of pretty close to 19,800 pounds. Let me double check that. Excellent. Nice job. We're off by just about 1 pound or half a pound from my question that doesn't have any round off error. So now that we have the magnitude of vector u, so this crane on the right is having to exert a total number of force of 19,784 pounds, 0.95 pounds in that angle of 45 degrees. So now, how much force is the other crane having to exert? How do we find the magnitude of vector v? Now that we know the magnitude of vector u. Plug it in. Plug it in. Come on. All right, so what's this going into? You want to use this one? Okay. So now this is getting plugged into, I would say maybe arguably slightly our simpler of the two equations.
Why wouldn't we plug it into the vector v equals 0.7826 vector u?
You can't, that's post substitution, right?
Why wouldn't we plug this where?
The thing about vector v equals, yeah, that.
Yeah, why wouldn't we? That's a much better choice. Okay. So vector v, the magnitude of vector v is equal to, thank you, 0.7, 826 times 19,784.95, granted our slightly rounded off version for the magnitude of vector u, and the magnitude of vector v is equal to, excuse me, I can't hear him, 15,000.
483.707.
And survey says, I like it. All right, so we got two cranes, one giving a force on its cable of 15,483 pounds, 0.7, and the other crane exerting a force of 19,784.95 pounds to hold a single object up of 20,240 pounds. The sum of these two are well over the 20,000 pounds, but right, we have a lot of that energy, a lot of that force is being exerted in the horizontal direction because just the orientation of the cranes and where the object is in space. But at that moment in time, each of these cranes have to pull that much force to keep that 20,240 pound object stationary. That's pretty cool. Bam! I would love that question.